Hi, I'm Chicha Gustiani. I would like to give a quick introduction on a package I've been built, so-called VQD, or virtual quantum device. So this package is an emulator for quantum computer, but it's detailed and give realistic error models. And this work was with collaborations of Tyson Jones and Simon Benjamin. And if you like to check on the source code, go to this QR code. Okay, so the aim of this package is to provide realistic error models that are based on actual quantum devices. So the aim is to give intuitive usage where the user can just do plug and play. And of course, the users need to have a little bit of knowledge on this quantum device. So the user inputs the native operations of the quantum device, and the quantum device is tailored to certain parameters. So here the parameters are quite intuitive and frequently found in experiment papers or in calibrations. For example, the T1, T2 times, the frequency of the qubits, the gates, fidelities, and harmonicities, and so on. And from these parameters, the VQD will tell you what are the noise decorated operations. Okay, so here the users need to follow the native operations of the quantum device, and these operations are not limited to just quantum gates. For instance, in case of neutral atoms or trap ions, the users also need to shuttle the qubits, basically. So this shuttling process induces errors. Here we consider quite extensive error models. For example, we have the free induction decays errors, which is T1, T2 errors, the stochastic Pauli's, the crosstalks, the of resonance-derived oscillations, the leakage errors, the spam errors, the coherent errors, and so on. So this, as the user has to follow the native operations, then each native operations has definitions, has assumptions of this error model. So we hope that if you follow this native operations, then the assumptions can be maintained more or less. Okay, so here we have 5 types or virtual quantum devices, which are based on actual quantum devices, and I would like to thank all these wonderful people to make all of this possible. So we have ion traps, which is multi-nodes ion traps that are linked by photonic links, and the user can have multiple nodes of ion traps, as many as they want. And we have nitrogen-vacancy centers, NV centers. We have superconducting qubits, we have neutral atoms, and we have semiconductor spin quantum dots. Okay, so the architecture of the software, the VQD is built on top of the Questlink. So we use Questlink to define the VQD, and the Questlink provides the interface to Quest, which is written in C. So this is a performance computation. Then the basic operators or the linear algebra operations, the multi-threadings, the GPU accelerations are happened in this side, and the Mathematica interface is done by the Questlink, and also defines a high level common operations. And up to this point, everything is hardware agnostic, and the VQD encapsulates everything that is hardware dependent. For instance, the error models, the native operations, the configurations of the virtual device, and the visualization related to the hardware, for example, the location of atoms, ion configurations, they're all defined in this VQD package. Okay, so a quick introduction how to use VQD. Okay, now we have this empty notebook, and since we need quest link, so we have to import the quest link first. We can use this website, get a theory. Okay, this is loading the quest link. And yeah, this is some warnings or alerts if anything's from the package of the quest link. And then you create the linker. For example, you can use a pre-compiled linker to the quest. Create download, so it will download the precompiled binary file depending on your operating system. So if you want to use accelerated GPU or multi-threading, that you have to compile the quest yourself and link it here. And then here we can use quest link, so you can see quest if it loads these modularities of the quest. And we do the same for the VQD. So you import the file, the VQD source code basically, and you can use it from the repo. So you go to this VQD repo and go check the source code of the VQD, and you can just load the file directly. So you do this, and yeah, it should give you the VQD functionalities. So you see that all these functions are anything that is hardware related, or like plot atoms. This is for the rebirth. Okay, now for example, I will show how to use NV centers. Let's say this is NV centers belong to University of Delft. So first you have to configure the device of this NV center device. So if you just generate a virtual device, you see that all these options values are not found. So we do not pre-configured with the values. So you have to put these options yourself. Okay, so if you can see from these options of functions, and you see that it has no definition. So for example, in this NV center or any other device of your interest, we give you a quick guide on how to use this device. So NV center has the characteristic of this central spin system, and this is the native operations of the device, and then this is the parameters. So for example, here we have the configurations of NV centers of University of Delft, and you can just copy this and directly load this command. Now you see this the default, it set default functions of the NV center Delft, and you see that we now have 6 qubits of NV center. And to generate, so this is the functions that will generate NV center device. So to create an instance, you can call the function now NV center. Let's see, I have a device called NVC, and this will generate the virtual device. Okay, It's just some type of function, and you can override the this default values. For example, if I set like fidelity of init, let's say I can have 100%, then this will give you the epicenter with overridden value of fidelity. Okay, let's say I now what I want to do is I want to create a circuit, okay, and we can have a quick look what are the native operations. So here there is initializations in the qubit 0, and then all the rotations and the 2 qubit gates. So let's say I want to put init on the qubit 0 and rotate qubit 1 with value theta, let's say. And then what else we have? This CRX, CRY, let's say CRY 0 and 4. This is our circuit, and if you want to see the noisy version, then you can call this function insert circuit noise. And if you forgot how this works, you can just see press this down arrows. You see, you first specify the circuit and then the spec of the device. So we have the circuit here, and then the device is NPC. Yes, you see that it will tell us gates which are not supported. Okay, so we put an error here. So it's supposed to be, you have to specify it's a parameterized CRY. Then it will tell you the all these noisy versions of the function of this circuit. So if you see draw circuits, how it looks like. Okay, so it tells you this is the noisy versions of just these 3 operations. And this insert circuit noise, you have to it gives you the schedule of the operations and also the noise. Okay, now how to run this noisy versions. You have to create, see, for example, I create to the simulation, I create a density register. Say density qrex and specified number of qubits. And yeah, so if you and then you just do apply circuits, and you see that you can, if you forgot again, check this first, the qreg, and you specify the noisy version. So here if you want to run the noisy versions, you have to extract this scheduled operations into just operation that is runnable on the questling. So to do that, you have to extract the circuit, and you will see that now this is just runnable circuit. And to make sure everything is in the language of a questling such that it is simulatable, you have to do this. Replace all the aliases. So this of the aliases define only on the hardware, and it will be converted into this questling native functions. So you can say true, then this should be runnable. So if I apply circuit, now I say the noisy circuit. Okay, and yeah, it contains numeric parameters, and you see that we did indeed have this theta undefined. So if I define this, let's say theta to be pi over 4, then we should be able to run. Yes. So now if you want to see the density matrix of this row, this is what it shows. Okay. And to see more details on each device, I would recommend to go to the example of notebook. So here, if you go to the device of your interest, it will tell you what is the characteristics, okay, and how to use this, and the functions, the key functions. For example, here in Rydberg device, you can see the plots of the atoms, and then it gives you a basic example how to use this, the native operations. It's a little bit more extensive for neutral atoms. And then if you go to this quantum dots, see, these are the native operations, the quick characteristics of the architectures. In this case, we have the Delft version, which is a linear architecture, and then if you want to see the trap ions, then it's an entire different characteristics. So here an example of two traps, I'm calling them Alice and Bob, so you can have as many nodes you want actually, and then you have to follow all these QCCD ion traps, which has zones of different operations. You can see that in ion traps you can have different multiple nodes, and on each node has different number of qubits. So you see, like here I have two nodes, Alice and Bob. One can also add the Charlie, and so on. Okay, and to use this is like a good way to have a quick look if you forgot what are the native operations. But to use it in really more details, I recommend to check on the example of the notebook. For example, go back to the Rydberg, and this will give you the notebook example, and the PDF will tell you how the output should look like if you run the notebook. Here, the Rydberg, you need to follow the blockade rules. Basically, if you want to perform 2 qubit operations between two atoms, then the blockade radius should be overlapping to each other, and otherwise you'll receive an error. So this example will tells you, guides you, like quite extensive example, and as well as the results that are shown in the paper. For example, yeah, this is quite long, so I recommend you to check. For example, here I already downloaded, let's say, this NV Center. Then if I load this, then it will tell you like the basic usage of the device. For example, if I want to perform let's say the controlled XY, and it tells you the precompiled gates. So here, if I want to initialize the spin qubits on the nuclear qubits, remember that the initialization is only happen on the center qubits. So what happens if you want to initialize the other qubits, then you have to swap. So you initialize the electrons and then you swap it to the nuclear spin. So for example, this is the sequence that you can use, and then this is the operation that you can do if you want to initialize a qubit 1. Here is another example. For instance, if I want to initialize the entire 6 qubits, then you can see this is one way to do this. And there are other useful functions that you can use. For example, this create random mixed states. So here in this example I create random mixed states, and then I check the fidelity of the zero state. So we have 0.016, so it is completely mixed and random of the 6 qubit density matrix. And if I see that, now I will show you if I can initialize our 6 qubit random state using our function. So we see that this is the initialization circuit, and then what I showed you that this would be the noisy versions of initializing the 6 qubit state. It is a really long sequence, but we will see if we actually can initialize our 6 qubit register. Yes, so we managed to initialize with fidelity 0.93. Yeah, so all of these notebooks helps you to guide on each characteristic of the virtual device, because each device is really different to each other, and we try to mimic what happens in the reality, so the user can experience all this one step closer to the actual device compared to just the gates that we usually use. And yeah, I would recommend this checking on each notebook. Go through the notebook, and it also tells you how we obtain the results on the white paper. For example, for NV Center, we provide you how to perform the dynamic simulations of this BAC simulations, and yeah, it's quite extensive example. So I hope this helps. And